we're going to record those sessions. So if you don't feel like speaking up or asking a question directly, just ask me and I can ask in your name, or just, tell the question without naming you. So those videos will be available afterwards on the Knowledge Graph conference library. And yeah, I guess that's pretty much it. If you have any question, please ask them in the chat. I will phrase them, so tell them loud so it can be in the recording. And you can also ask me on Slack, or I don't know if you've seen, but we have also a GitHub to use issues with. Okay, I guess that's pretty much it. I'll leave you the floor, Alessandro.
Cool. Thanks, Matthias. So I will quickly start by, first of all, thank you, everybody, for joining us today, and of course for the interest in this book, because differently than the other book clubs, in this case, I mean, there are also the authors in this one. So thank you for joining us, but mostly for getting really an interest in the book. So I will do a very quick introduction. Then we will start, let's say, going through the main concept of the chapter 1, and after that, we will do the same for the chapter 2. But before moving, I would like just to, let's say, set the ground by mentioning a bit what are the basic ideas or the main reasons that are behind the book, because what we were trying to do, what we are still trying to do with this book, since this is still a work in progress, is to approach the knowledge graphs problem from let's say application perspective. So our background in terms of let's say work background is that we are coming all from Graphover, where we help our customers to succeed in general in the graph space. But very recently, let's say in the last 5 years, we are literally helping them very often in succeeding in building and analyzing knowledge graphs. You will notice along the entire book this origin of our history or our experience, because we are not coming from the research industry. We were expert in graph theory and graph modeling and graph, let's say, powered machine learning. And in the last 5 years, as I mentioned, we are working with the concept of knowledge graphs. So this will justify many of the things that you will see today, but of course we would like to also embrace other different type of technologies, not coming directly from the let's say from the classical graph database space. So this book, as I said, I'm to be a very practical reference to help practitioners like us 5 years ago working with knowledge graphs effectively. So we try in this book to cover 3 main critical aspects. So first of all, the why, so understanding where the knowledge graphs can solve critical problems, so why they exist and which kind of problem they can solve. Then how to build a knowledge graph, so how to convert different data sources that are heterogeneous in a knowledge graph that can be used for several purposes. And of course, once you have this knowledge graph and you navigated it, how to analyze, so extract a certain type of insights out of it. So that's mostly the 3 major areas that are covered in this book. So it is divided in 3 parts. The first one is, of course, an introduction in which we set the ground, explaining what is a knowledge graph, at least from our perspective. As you maybe know, there are many definitions of knowledge graph taken from different sources. So we also have our own definition, of course, based on what we think is a reasonable definition, but of course is subjected to let's say to opinions, I would say. Then the second chapter that we will see today is related to intelligent systems, because as I mentioned, it is let's say a knowledge graphs applied book. So the main applications that we would like to mention and to drive the entire let's say book are intelligent systems, and the specific type of intelligent systems that we will see. After that, we will start immediately with covering. So once we cover this why part, we would like to cover immediately the building part. Of course, in the first part of the book, we would like just to build from scratch a knowledge graph, starting from structured data sources, ontologies, for example, and other structured data sources. And in the part 2, instead, we will cover how to build knowledge graphs out of unstructured data sources like text, mostly, and not only. So how to literally take this text and extract entities, relationships, connect them to ontologies, and so on and so forth. And finally, in the part 3, we cover the analysis part. So how to extract relevant insights out of these knowledge graphs that have been built, across the entire book. So that's how it is structured. And of course, this is not complete. As I said, currently we have let's say the chapter 1, 2, 3, and 5 that are completely published and available in the MIP. We have almost done also the chapter 4, and we will cover it in any case, even though you cannot read it, but we will discuss about its content in these sessions. And in terms of what are the main goals of this session. Of course, first of all, we would like to have fun, because this is definitely not a topic for everybody in this call. I asked Matthias to give us this opportunity, because I think that all of us share a same interest, in a specific area that is quite big and that is growing quite fast. So we would like to have fun with all of you, having an interesting discussion. Specifically, I would like to challenge you. I mean, we would like to challenge you many times, with our definitions, or we are thinking about knowledge graph and the word around, and feel free to argue against this, because this would be really the benefit of this discussion. And of course, we would like to gather feedback. I think that here there is a great opportunity for all of us, and even for you, to be part of this book production, because this will allow us to literally gather this feedback and make this book better, hopefully. So that said, I will let Giuseppe, that is the main author of the chapter 1, to introduce the chapter. And again, feel free to interrupt us whenever you want to ask questions. Otherwise, we will leave some time at the end to ask any question that you want. That's it. Giuseppe, I will stop sharing.
Thank you very much, Alessandro. Let me share the screen. Are you able to see the slides?
Yep.
Yes, we are.
Okay, cool. So let me start, and thanks Alessandro for the introduction. And as mentioned by Alessandro, actually the chapter 1 discusses the topic of what is a knowledge graph. But before providing our own definition that we would like to discuss with you, I would like to emphasize the topic related to the paradigm shift that characterize the modern data-driven applications. Because as you probably know, traditional systems are characterized by specific features related to the data, which includes, for instance, the adoption and the ingestion and processing of homogeneous information. And this information is usually structured in a rigid way. Let's think, for instance, about relational databases in which extending the schema in terms of new tables or in terms of new fields, it's not an easy task. And usually these traditional systems are characterized and are developed for a very well-known purpose. And in many cases, the insights that we want to get from this information is clear in our mind, right? So these type of systems are not so feasible for knowledge discovery. In most of the cases, considering these unflexible flexible features of the data, the intelligence and the intelligent behavior are usually encoded and directly incorporated repeatedly in the applications developed on top of this data. But currently, for modern applications, in particular for complex domain, actually we need different type of features for developing advanced systems. Because in many cases, let's think, for instance, about the healthcare domain. In many cases, we should be able to treat heterogeneous data, right? So basically data coming from multiple sources that are available in different formats, from different, that are stored using different types of technologies and etc. In many cases, this is a never evolving information. Let's think, for instance, some crisis or critical situation like the pandemic, which requires to integrate and store new information in order to enable advanced analysis for a specific task. So basically, we need a tool that is enough flexible. It is able to meet changes in the context. So another main feature is the complex domain, because in many cases we do not have a specific purpose, right? But we should be able to manage a complex situation, and at the same time, we do not want only to extract insights that are already available in our mind, but we would like to perform knowledge discovery. And for instance, and for all these features, we think that the knowledge graph is the right tool, is the right framework in order to enable of these aspects. And for knowledge graph, the intelligent behavior in terms of in terms of reasoning and meaningful data is directly encoded within the knowledge graph. So after this premise, that I think it's quite important to understand why knowledge graphs are really important for developing modern applications, we will provide you our definitions, right? And first of all, I would like to read to you this definition, and I will try to provide you some motivations behind this definition, and also maybe create the conditions for a bit of discussion around this definition in order to get if it's too complex or if it's missing, or if we miss something, and etc. But I started reading it. So basically, according to our perspective, a knowledge graph is a never evolving graph data structure composed of a set of typed entities, their attributes and meaningful name relationships. And they are built for a specific domain from both structured and or unstructured data to craft knowledge for humans and machines alike. So basically, we believe that this definition includes all the main characteristics, all the pillars of the knowledge graph. And we believe that all these pillars becomes really useful because they can be directly exploited in the use cases that we propose in the entire book, right? So this is the main motivation behind the knowledge graph. And I'm really curious if could be interesting to discuss with you about around this definition, right? So having a conversation on that. I don't know, Matthias, if you would like to get some questions from the chat.
Yep, they are already arriving. So let's start with Marc-Antoine, who is asking, so multi-typing as in RDF. So Marc-Antoine, do you want to speak up, or because it's
yeah, just I saw typed entities, and I was wondering if that entailed single typed or if you allowed for multi-typed. I'm also, that's a different question, but are entities always well defined and well identified is something I'm personally interested in, but that's a different topic.
Well, actually, in regards to set of typed entities, ideally, we would like to set different types of entities according to the domain that we want to describe, right? So basically, according to our perspective, typed entities means that we assign a specific type to a node, for instance, in the knowledge graph. So basically, we include people, organizations, or places, depending on the domain that we want to describe. And to these typed entities, we want to assign specific properties that characterize the different dimension that this entity can have. So basically, when we model knowledge graph, we would like to create the condition in order to convey this type of information. I don't know if I answered to your question or.
No, in RDF, we're allowed to give multiple types and hence to give multiple sets of properties to a single entity.
And this can be done also, I mean, let me say that this is a generic definition that is not based on any specific implementation.
Right.
You know, so this is, I mean, we are still not talking about RDF or LPG or level.
No,
so
I understand.
Here, what we meant for typed entities is just that each entity should belong at least to a type. It's not an entity that could be whatever, you know. So as Giuseppe mentioned, there could be a person, but this person could be also a manager, could be also at the same time something else. So the important thing in the typed entity part is that they should be able to be classified somehow as belonging to at least a specific type. Cannot be, okay, it's an entity, whatever it means, you know. So that is the definition here. Then there was another question about the domain single versus multiple domain. Well, I agree that you know, you can have a knowledge base that is related to many multiple domains, you know, but in reality, based on our experience, the most successful knowledge graphs are mostly related to a specific domain if you would like to serve certain specific purposes, you know, rather than being Wikipedia, for example. That is definitely a good source of knowledge and we use it quite a lot. But at the same time, you know, when you go in detail and you would like to explore specific domains like law enforcement or like healthcare or other, Wikipedia can solve partially your issue because you need a very specific type of knowledge where, you know, as in the examples that we will see across the book, you know, the type of information that you need is not for the broader public. You know, you go very much in detail in that specific domain, and a generic knowledge cannot solve many of the issues that you have because it is by definition generic. You know, that's why we added this domain concept as a part of the definition. Does it make sense? I don't know who asked it.
Yeah, partly. So with domains, could you also see, for instance, in pharma, the research domain and the organizational domain? Or would you then throw that on one big pile and say it's the pharma domain?
Well, the answer depends on the usage of the knowledge graph that you have to do. You know, as we will see later, for example, in the chapter 2, but this is true for the entire book, you know, we are against a sort of bottom-up approach in which you take all the data that you have in the company, you put, let's say, in a blind way inside a knowledge graph, and then you build, you know, your applications on top. We are more in favor of a different type of approach in which you start from let's say, the business needs, you know, for understanding of why you are building this knowledge graph. And specifically, you know, you can have multiple, then you can have multiple knowledge graphs at that point, you know. So even though in a company, like a pharma company that you were mentioning, there are researchers as well as other tasks, you know, like selling these products everywhere. And of course, you could need a knowledge graph even for that. We would not recommend to have a single knowledge graph covering the whole of enterprise, you know, in that sense. So you will have a knowledge graph for making your, let's say, drug reproduction better, just saying, you know, another one for making your, I don't know, logistic better, for example.
Yeah. No, I understand that. Although I would argue that Wikipedia or Wikimedia also has a business need, and Google also has a business need, that they served by these knowledge graphs.
Absolutely. No,
or the business needs. Yeah.
I totally agree.
Siri, for instance. Yeah.
But they serve a specific purpose that is literally their domain, you know, in the sense that even a broader domain can be a domain. You know, we are just saying that they cannot serve all the domain just because they are generic. You know, definitely I don't think that a pharma company will use Wikipedia as the main source of knowledge because it is too generic.
Well,
they will use
some specific for genes, for instance, there's this big effort to get all gene information in Wikidata. I think it's used in that way.
Could be. I mean, in the future, who knows? Maybe that this will become a major topic, and it will be, let's say, Wikipedia will be extended also with this type of information. I mean, nothing prevents them to be even specific. But does it make sense to have something that contains the full knowledge of the human? You know, I don't know. That's just the thing. But really, the domain could be even interpreted here as a generic domain eventually.
So do we have time? Do we have time for another question, or do you want to move on? Sure.
No, please go ahead.
No. Yeah.
So I think we missed one question about a specific choice of a verb. The verb craft is Sarah is asking the choice of the verb craft in craft knowledge is interesting. She's curious about why this verb was chosen. Do you have?
Yeah, actually, because we consider, let me say, a knowledge graph as something that is a sort of artifact, right? So basically, we craft knowledge, so we compose actually this knowledge for both humans and machines. So that was the idea that we have in mind. We want to stress this fact of composing and crafting the knowledge in order to prepare it for humans and machines.
And also I like that it's not a linear process. You know, it's not something that you have a clear idea from the day one. You know, you literally let's say curve it from let's say from several sources of knowledge. Sorry, Zara, you wanted to say something.
Yeah, I think that makes sense. Another verb I often use when I talk about what knowledge graphs do is like represent knowledge. So that was interesting to see, you know, craft, and I get where that's coming from. I just was curious to hear your thoughts on that. So thanks for sharing.
Okay. I don't know if you want to intervene. There is a discussion in the chat, but I think it's pretty much answered. Okay. There is a question about how many domains specific knowledge graph. I think Ebert, well, I can't pronounce the name. You can speak up Mark Ebert. I only have the
yes,
M.
Mark Hebert, yeah.
Yeah.
That's good. Well, I'm trying to build out knowledge domains and knowledge graphs here in a small city in South Florida, and you know, encountering the difficulties that one would expect, and just trying to get data out of one format and into some kind of triple format. But I like this idea, and I'm just curious, like, are you describing a specific domain structure that is contained, or is it you know, reachable from other domains, through inference and things like that?
Well, actually, in the book, we will present a lot of examples in the healthcare and biomedical domain, but actually we use the specific, and we will discuss specific use case in this domain, because I think that the domain is enough complex in order to make the concepts that we discuss in the book applicable also to other domains. This is one of the reason why we choose the healthcare domain for most of the examples. And on the other side, this is a domain in which a lot of data is available, right? So also a lot of complex data. So in order to enable our readers to replicate our code examples provided in the book, we chose a domain in which there was a lot of data, right? And but ideally, all the concepts that we discuss in the book, we keep in mind that they can be applicable also for other application domains.
Understood. I'm just curious because the way you describe it now in this discussion, you're saying the healthcare domain, but even that crosses, subdomains. So
yeah, definitely.
I'm thinking about how you construct it so that one domain is aware of another domain for the purposes of linking things together, right? Which is the purpose, right? To find the links between elements. So it's one thing to dive into a morass of large data on, let's say, pharmaceuticals to understand things, but then you also want to be able to see patients, outside of the pharmaceutical column or vertical. So I'm wanting to make sure I understand that, because I'm looking at reading this book when it's available and applying what you're talking about now to the domain of cities, which have multiple verticals throughout it, not the least of which is citizens and governance and things like that. So being able to harmonize the information so that one domain can be looked at and then inferences made out of that domain into other domains. For instance, just the clerk's office in our city manages all the documents for the city. So that's textual data that needs to be, pulled apart and made rational. But then again, if somebody is living on a given street and they want to know, well, what construction happened here in the last 30 years, they want to be able to go look at documents. They want to look at records of permitting and things like that. Maybe they're looking for redress from the government. They're trying to cite examples. They need to, pass through a number of domains to collate that type of information.
Yeah, I think sorry, Alessandro, go ahead.
No, I was just gonna answer very quickly so that we can cover this broadly even in another moment. But really what we do generally in this case is to literally search for reference, in the sense that, for example, you were naming the street names and stuff. What we do generally is to, whenever we have to merge different knowledge or we need to link different knowledge bases, what we do is to try to get through certain, let's say, dictionaries or certain references, where easily you can find connections among elements that are even referred in a different way. For example, for the name of the street, we use nominating, for example, as a sort of reference where you can put the name of the street and you get an ID that then can be used on any knowledge that you have to try to find connections. Unfortunately, there is no standard way, I would say, rather than searching for cross-reference, some Rosetta Stone that will allow you to find connections among the different entities. No other ways or standard as far as I know.
Understood. Thank you.
Okay, I think we don't have any more questions. We can move on to the next.
Okay, thank you, Matthias. So basically, I will go a bit faster. I mean, because behind, as I said before, behind this definition, there are what we think these are the four pillars, right, that characterize the knowledge graph from our perspective. So basically, a knowledge graph-based application should work with dynamic information in an ever-evolving environment. And from a graph perspective, it means that should be able to add, update, or delete specific graph structure in terms of nodes, edges, and properties, but also in terms of graph-based data model, right? So basically, we would like to add multiple nodes of the same type, but also add a new node type in a very straightforward way. And in a graph-based structure, we are able and would like to perform also some specific algorithms that, for instance, enable us to detect the most influential nodes, or to apply network analysis and detecting, for instance, the shortest path between two nodes, and etc. So this is what we intend for evolving graph data structure. The other main features is the semantics, because as you probably know, in traditional databases, actually, they often neglect the meaning of the data, right? Because usually the meaning of the data is clear in the mind of who designed the database, but it's not explicit in the data. When we create a knowledge graph, we want to build a knowledge infrastructure that is able to convey the meaning of the data in an explicit way. In regard to the integration, this is another very important dimension of the knowledge graph, because we would be able to integrate information coming from multiple data sources, both structured and unstructured data. Because in the case of knowledge graph, the meaning, the meaning behind the information is the key aspect, right? So basically, with the graph structure, we are able to overcome types, formats, the provenance of the data that can be stored actually in the knowledge graph, but it's not so important in terms of modeling of the graph. So basically, we want to create this bridge between information from multiple data sources. And regarding the knowledge crafting that we mentioned before, we think that this knowledge can be directly exploited by humans and machines, because humans can perform analysis, can visualize the knowledge graph, can perform query on the knowledge graph. And with humans, actually, we do not include only graph technology expert, but mostly domain experts. Right, so basically people that is expert in the application domain and that can use the knowledge graph for its goals, for its specific activities, and etc. On the other side, also the machine can learn from this craft knowledge, because, for instance, we can apply reasoning to derive new knowledge in a deductive way, or we can apply specific rules to get new knowledge. But on the other hand, we can also apply inductive approaches, and later Alessandro will provide details on that, which enable us to perform machine learning or also representation learning techniques on top of the knowledge graph in order to learn in an automatic way the most important features of the knowledge graph. And this is a way in which the machine can learn from this network structure. As I said before, actually, these pillars can be applied in some specific knowledge graph-based applications. And actually, we can apply the principles that characterize these applications also in other domains, right? For instance, a 360-based view can be really useful in the healthcare domain, because it enables us to apply precision medicine approaches or to define personalized strategies for the patient. But potentially this view can be applied also for a customer of e-commerce platform, right? So this is the idea behind this type of knowledge graph based applications. In the specific case of the healthcare domain, we can perform drug discovery and development analysis, exploiting, for instance, graph-based machine learning techniques, also reasoning, in order to infer new information that can be useful in the drug discovery, for the drug discovery task. And another interesting application could be the compliance management, right? So basically, this type of approach can be employed in the healthcare domain, but basically also in all the other domains that require to satisfy, for instance, specific regulations, and etc. And in this case, the main features could be the integration, the capacity of integrating multiple sources, the capacity of monitoring the evolution of this information, and applying, as I said before, complex rules to satisfy the compliance. And last but not least, using the knowledge incorporated into a knowledge graph, we can develop conversational AI systems and recommendation systems, because we can exploit the content-based network provided by a knowledge graph, and also the contextual knowledge that can be useful, for instance, to ground the interaction between a human and an intelligent agent that is usually an intelligent advisory system, right? So basically, it should be able to interact with the human being, and this interaction can be enabled by the knowledge incorporated into a knowledge graph. So this is an idea of the potential applications that are also presented in the first chapter, right? Describing each application in terms of challenges and in terms of knowledge graph-based solution that can be applied to tackle these specific challenges. Before asking questions, I would like also the last aspect that is discussed in the chapter 1 is related to the knowledge graph technologies. And on this topic, actually, I will ask feedback because obviously we identify these two approaches as the most prominent framework in order to create a knowledge graph, in order to query a knowledge graph. Here we put some of the features of each of these approaches. And in the case of resource description framework, the focus, the main aspect is related to the knowledge representation. And according to this perspective, the graph can be seen as a collection of statements. And one of the features of RDF is also to ensure the semantic interoperability, for instance, in the linked open data cloud. And the core of the intelligence is the reasoning, right? So incorporating ontologies and schemas like OWL and RDFS, we are able to we enable the reasoning, right, on the data in order to derive a new knowledge and new statements. And the query approach in this specific case is characterized by the statements manipulation. So basically, in the spectral query, you define the statement patterns that allow you to get the information you are looking for. From another perspective, the label property graph is focused on a graph-based data structure, right? So for instance, the data is explicitly representing using nodes, relationships, and properties. And regard to the properties, this is an important aspect because before RDF Star that has been released a couple of years ago, you are in RDF, you are not able to model the properties of the relationships, right? You should apply some acts to RDF in order to represent relationship properties. And according to the label property graph, we already said that this approach emphasizes the features of the graph data, and the core of the intelligence considering this graph data is to apply graph-based algorithm and machine learning in order to get specific insights from this data. And in the case of the query approach, basically, for instance, a query language like Cypher enables you to have a transparent interaction with the graph structure. So basically, you define specific graph patterns in Cypher in order to get the information. And considering the main features of each of these approach, the high-level approach that we will use in the entire book, our main idea is just enough semantics. So basically, considering the use cases that we will discuss in the following chapters of the book, we decided to adopt the LPG approach as the core approach in order to create, for instance, and to query and to analyze the knowledge graph. And we decided to incorporate specific RDF features, including, for instance, the reasoning, only when necessary. So for instance, in the next meeting, I will show you how we can apply the reasoning for a specific use case in the healthcare domain. And so basically our approach is to iteratively and progressively expand the expressive capabilities of our knowledge graph, so of our knowledge infrastructure, if it is required by the concrete use cases. So we decided to adopt this approach because we believe and we noticed that for the use cases that we discuss for the entire book, this was the most efficient and effective in order to get interesting results. And on this topic, I would like to have some comments and feedback and suggestions, because we are open also to update this approach according, if there are, for instance, some specific use cases in which this type of approach to the problem, it's not the effective one. So let us know if there are some comments or...
There is a few discussions in the chat. I will take a few questions. I just want to make sure that you have the time to go over all your content for this session. So please let me know if you...
Yeah, I mean, I think that we can take some questions. I mean, my part will be faster if needed, and not a big deal.
Okay, awesome. So I guess the first one was about how much would you say that knowledge graph act as a base for further analysis? So machine learning on graph, and how much is just about querying the graph? And I guess, Alessandro, you already answered this question in the chat.
Yes,
so
I mean, the quick answer is 80-20, 80 for querying right now and 20% for machine learning. Unfortunately, there is a lot of effort going for building these knowledge graphs in companies, you know. So the first thing that you can do is just to evaluate that what you built is correct. And later on, this will evolve in more advanced tasks. But for the majority, it's really just building and querying right now.
Yeah. Could I follow this up with a little question that fits the slide we're currently seeing? Talking about just enough semantics and having touched on RDF star and its possibilities just a minute ago, will you in the book touch on how to best model certain types of relations in RDF versus level property graphs? Because the problem I'm having right now, and I'm a total newbie, or I have been a total newbie to graph modeling. I'm from the statistics domain, more or less. I'm having a hard time trusting in my own solutions of what I came up with to model relations like A does B in the context of C with tool D. And in RDF, which I am not proficient in, I believe reification is the right thing, as in having a statement and then connecting that statement to an entity. But in labeled property graphs, there is no such easy solution, as far as I know, and I'd be happy. We don't have to expand on this right now, but I'd be happy to get somewhat of an answer to this type of questions in the book, like representing complex statements in a graph.
Yeah, I think that this is a good point for us, Giuseppe. You know, to see how these specific concepts that are canonized in RDF could be easily translated in the LPG case. So this reification, for example, you know, and the way in which this can be. I think that we can easily find a way for converting them in LPG for sure. But of course, not the time here to discuss. But absolutely, we can cover this even next time, or even you know, in the chat on Knowledge Graph Conference Slack, if you want.
I'll also happily provide examples and my example solutions.
Perfect.
Yeah, it could be really useful.
We actually have
There was another interesting question. Oh, sorry.
No, I was just saying for Johannes, this is the kind of stuff you can expand the discussion on the KGC community on Slack. You're going to have plenty of people to also answer and join the discussion there. Yeah, Alessandro, there is another question.
Yeah, there was another question about semantics stored in the graph.
Yep, so that was mine actually, I think.
Oh, yes.
It's about, you know, if you use RDF, you're going to have the data part that is in RDF, but also the semantics of the relation that is also represented in RDF. So everything is in one big graph, and the description of what does mean a certain relation is just another part of the entire graph. And I guess with label property graph, you cannot have that. It's more encoded in the framework that provide the LPG. So which one do you prefer, for what reason, or which do you, based on your experience, which one is more used than the other or something?
Yeah, actually, as you said in the RDF, you can specify the meaning of a relationship, right? So for instance, you can define, for instance, that a relationship is the inverse of another relationship. So you can also describe the transitive relationship in terms of, for instance, there is a child, right? Is a transitive relationship or something like that. Actually, there are some, for instance, plugins like neo-semantics that enable us to encode this type of behavior also within the LPG. But it depends on the use case, right? For now, according to use cases that we propose in the book, this type of explicit information in terms of semantics. So for instance, these relationships is the opposite of this other relationship. It's not a strict requirement, but I believe that for some other use cases, it's fundamental. For instance, if you want to design an ontology that cover the full knowledge that is related to a specific domain, the fact of specifying these relationships and the meanings of these relationships can help a lot, in particular for agents that can automatically surface this knowledge, make explicit this type of meaning and semantics behind the relationships could be really useful. So I think that it depends from the use cases that you propose. But in the next meeting, I will show you how, for instance, we can automatically exploit maybe a simple reasoning, but just exploiting the subclass relationships in order to get the information in an automatic way without explicitly describe the traversal of the graph, but using the reasoning features of this neo-semantics component that allows you to use some of the features of RDF in LPG.
Okay, thanks. That makes sense. Maybe Alessandro, do you want to move on, or do we take other questions?
Yeah, no, I will just move on. I would like just to answer quickly to a question from Quinton about Cypher rebranded to graph query language. As far as I know, this is not the case. They are also exposing an API that is based on GraphQL, but Cypher is the main language for querying the graph database. So as far as I know, but I mean, it's interesting that you mentioned Rick Van Bruggen, because I don't think it is mentioning this explicitly, but I will investigate with him directly since I know him personally. So I will double check that he's not just sending the wrong message, or maybe that I'm wrong and he's sending the right message, but I don't think so. Okay, so we have just 10 minutes and I would like to give space for some further questions. So I will be super fast in this part because the chapter 2 is relevant because since, as I mentioned before, this is a knowledge graph applied book, so we wanted to specify which kind of applications we are targeting, because as you maybe know, because you are in this field, you know, you can do many things with knowledge graphs. So specifically, we are targeting intelligent systems, and even not all the intelligent systems, but a specific area inside the intelligent systems, because based on our experience, this is where we can contribute the most, at least with this book. So in general, we are referring to intelligent systems as these systems that are able to connect users to, let's say, machine learning, or more in general to artificial intelligence, to achieve a certain type of meaningful, again, specific objective. So, of course, one of the main criteria of these intelligent systems is that they should learn by, let's say, interacting with the users, or by, let's say, acting with the users. So the meta map that we have and we propose for understanding the specific type of intelligent systems that you can empower with knowledge graph is this one, in which you clearly have at least, let's say, a set of sources. Of course, not all of them are canonical sources like documents or relational databases, but they can be also environmental information. And through, let's say, the intelligent system literally sends these sources. That means, literally ingest these sources, or just, let's say, monitor the environment or see what are the effects of certain type of actions versus decisions. And then, this intelligent system is capable of, as I said, to acquire this knowledge, to learn from the experience, and let's say that it can act in replacement of humans, or can suggest to humans which kind of decision to take. And that's where we make a very strong, let's say, distinction between the different type of systems. So we're grouping them in two main areas. On one side, let's say we have the self-driving cars, which means that these are intelligent systems in which the system acts in, let's say, on behalf of a user. So in self-driving car, the classical example, the car is driving by themselves. The user is just sitting in a car and waiting for the rest, let's say, for the artificial intelligence to do all the rest. But always in the book, we are referring to the intelligent advisor system. So that are systems in which let's say, the final result of the entire process is to advise the user. Again, if we would like to make the example that we used before of the healthcare, for example, what we would like the system to do is to suggest, for example, a treatment, or to suggest what is the alternative use of a drug, in a drug repurposing case, or to help a pharmaceutical company, to take a wise decision. But they will never take autonomous decision without, let's say, the inference, let's say, the interference of the user. So we will focus along the entire book on this area, on this type of intelligent systems, in which literally the system will never act instead of the user. They will not only interact with the user, but they will learn from the user. So they will literally take the feedback loop and improve the, let's say, the decision or the suggestion in the next time. Then, of course, for our purposes, we decompose these intelligent systems in two main major, let's say, elements. On one side, we have, of course, the knowledge base that you can immediately understand that will be represented by the knowledge graph later on. And then we have a reasoning engine. In that sense, what we did was to make a clear distinction between what we consider a deductive reasoner and inductive reasoner. In the deductive reasoner, that is really what is generally used in the RDF, for example, cases, what you have is that you start from, let's say, generic generic statements that are true by definition, and you deduct some certain type of specific statements. So, for example, if sorry, I'm not in the slideshow now. I noticed. If all men are, let's say, human, and Alessandro, sorry, all men are mortal, and Alessandro, all humans are mortal, and Alessandro is a human. Of course, Alessandro is a mortal. So you do this deductive reasoning. So you start from generic statement, and then you go down in a better, a more detailed, let's say, statement. The inductive reasoner acts on the opposite side. So literally, what we ask to this reasoner is to start from sample, from real, let's say, from reality, and make a generic statement. There is a classical example of someone taking out of a pocket a penny, another penny, another penny. So the inductive reasoner will think that all the coins in the, let's say, in the bag are pennies. So it tries literally to generalize the concept, looking at the outside outcome of certain, let's say, operations or of the reality, and then make certain assumption in terms of generalization of that specific statement. So it really, in this type of reasoners, make broader generalizations from specific observation. That is exactly the opposite of before. In that sense, there is some major differences in the way in which this happens than in reality, because in the previous case, as you notice, what happens is that we take the sources and we literally operate a sort of data model transformation. So we literally create, for example, this knowledge graph, and then from this knowledge graph, we are able to extract specific statement as before. In the case of intuitive reasoner, the process is a bit more complicated, because in many cases, what happens is that this intuitive reasoner literally create a certain type of models. Some of them can be easily stored in the knowledge base. In other cases, instead, what we do is to start from this knowledge base and literally operate with this intuitive reasoner that will create other knowledge base. But that's why the two arrows here, because literally we use the knowledge graph in this case not as a, let's say, the source for the direct reasoning, but in reality we use it to create models from let's say using intuitive reasoner. And this is the, let's say, when the machine learning comes into play to get this type of advanced analytics that we are interested in. We are running out of time, but something that I would like to mention last, because Matthias had already a good point about this. Is the way in which we acquire this knowledge. Of course, as I mentioned before, we are acquiring this knowledge from different data sources, but of course, this is happening because we have people, as usual, involved in this process. And Matthias mentioned, that something is missing in this image, and this is I think that this is true. We should make this more clear in our head, because we mentioned that what is missing is the ontologist, for example, is the knowledge worker, someone that is literally creating the knowledge. This is true, absolutely. We should add this. In our head, it was in the domain expertise, because we believe that the domain expert are literally the owner of the knowledge, in some way or in many cases, because they add let's say the domain knowledge to a process that otherwise could be very, very generic and could work for everything. But that's definitely a good point that we can make even more clear. And the last part is something that we discussed already about this bottom-up approach versus the another approach that we suggest that is based on this crisp data model that is more generic for data mining, but it could be applied even here. Unfortunately, we run out of time, but this is for a good reason, because we had many interesting questions from all of you. I think we have just the time, actually for nothing. But I think if you don't mind to write them down in the GitHub or on Slack, we will be more than happy to answer in an asynchronous way.
Thank you very much.